everyone, thank you so much for clicking onto the video. Here are today's learning objectives. So the first is to know that alkenes form polymers through addition polymerization, and then to know that waste polymers can be separated into specific types of polymer for recycling, incineration to release energy, and use as a feedstock for cracking. And then we're going to understand, in terms of the use of energy and resources over the life cycle of polymer products, that chemists can contribute to the more sustainable use of materials. And the last learning objective will be to understand how chemists limit the problems caused by polymer disposal by developing biodegradable polymers and removing toxic waste gases caused by incineration of plastic. Now we're going to look at polymers. So polymers are long chain molecules that are made up of many small molecules, which we call monomers, which are all joined together. So things to remember are that they're long chained and they're made up of monomers, which are joined together. And polymerization is the process in which a polymer is formed. And there are two types of polymerization. We have addition polymerization and condensation polymerization. So right now we're going to look at the addition polymerization. Now we're going to look at addition polymerization. So addition polymerization is where many monomers, which in this case are alkenes, because we actually make these polymers from alkenes, are joined together to form a long chain molecule, which is the polymer, and the polymer is the only product. We use the presence of a high pressure and a suitable catalyst. Addition polymers, or we can call them polyalkenes, are formed. Addition polymers, which we call polyalkenes, that are formed are unreactive, and this is like alkanes, because of the strong carbon-carbon single bonds and carbon-hydrogen bonds. And so it takes quite a lot of energy to break them, and so these addition polymers are quite unreactive. And you also need to know that the knowledge and understanding of the production and properties of polymers have developed over time. And two things you need to know about the intermolecular forces between hydrocarbon chains is that since the hydrocarbon chains are often very long, the van der Waals forces between the chains are often very strong. And so polymers have relatively high melting and boiling points, depending on how long their chain is. So if you have a shorter chain, then the melting and boiling point would be a bit lower. But if you had a very, very long chain, then it would have a very high melting and boiling point. Polymers, which have very few branches, are very compact, and so the chains can pack together very efficiently. And this means that the van der Waals forces between the chains will be very strong. So they can pack, and they're also very strong. And therefore, these polymers tend to be stronger and harder, because again, they'll have high melting and boiling points, and so it'll be harder to break the bonds. So we're going to look at these two examples. First, we're going to look at polyethene from ethene. So what we do is we have two ethene molecules. So we draw out two ethenes just so it's easier for us to work out how we form the polymer. And so what we do is just break the double bonds and add everything together. So we have carbon with two hydrogens, which is this bit here. But now I'm going to draw a bond connecting it to something else, so something imaginary. And then we're breaking the double bond, so this becomes a single bond. And then we have carbon and hydrogen. And then this forms a bond with this other ethene here. So we have another CH2, and then another CH2 because we've broken this double bond as well. Then again, we're going to draw a line, which basically just represents that we're carrying this on. And then we need to put some square brackets around. And then what we do next is we have to add in a little n. And this just indicates that this repeats and repeats and repeats. So this is actually a really, really, really long chain, but we're only drawing 4 carbons worth. And so this is why we put the n. And a use of polyethene, so that's what we've formed polyethene. And some uses is that we use them in carrier bags and also washing up bowls. And now we're going to look at polychloroethene or PVC from chloroethene. So what we have is we have chloroethene. So I'm going to draw out two chloroethenes. And this is going to do the same thing. So we're going to have carbon with. So now we're going to look at the repeating unit of polymers. So the repeating unit is the smallest group of atoms that will produce the polymer when repeated over and over again. So for example, if we looked at polypropene, so we have two propene molecules. And then we can form the polypropene. Remembering to put in the lines to indicate that it is a very, very long molecule. And then we put in some brackets and then the little n. And so to find the repeating unit, we need the smallest group of atoms that will produce this polymer when repeated over and over again. And so we can see that if we take this bit, actually this is exactly the same as this bit next to it. And so the repeating unit is just one of these, because this is actually a repetition of the repeating unit. So this is 2 times the repeating unit. And so we get that the repeating unit is equal to carbon with the hydrogen, and we need the methyl group, and then 2 hydrogens. And we still need the brackets and the n. And so this is the repeating unit, because we actually only need half of what we formed before, because it's a repetition. However, if you're told to draw one repeating unit, then we don't put the n, because the n actually tells us that it's a really large number. So if you're asked for one repeating unit, then you just have this thing that we've drawn but without the n. Now we're going to look at finding the repeating unit. So we need to be able to find the repeating unit from a monomer structure and also a polymer structure. So in the first example, we're going to find the repeating unit for this monomer. So we've got this alkene, and basically what you need to do is you need to imagine 2 of them joining together. So then what this would form would be you'd have carbon, you'd have 4 carbons, and then COOCH3, and then a hydrogen on this one, and then some more hydrogens. That one would also be a COOCH3. And then you'd have a CH3 here, and a H, and a CH3, and a H. So this would be the polymer that you would get. You'd kind of just think of this in your head. I mean, you can doodle it if you want, but it'll probably take you a bit more time. So if you do a quick doodle or just think of it in your head, you can then work out the repeating unit. So we can see the repeating unit is actually half of this, because it is actually a repeat. And so the repeating unit is 2 carbons, and we have a CH3 group here, and hydrogen. And then we have the COOCH3 group, and then a hydrogen. And so this is the repeating unit. And then for the polymer, we do exactly the same thing, but now it's actually a bit quicker because we've actually got the whole polymer for us to see. And so again, we can see that it's half of this. And so the repeating unit is 2 carbons, a cyanide, and 3 hydrogens. So that's our repeating unit. And one thing to note is that when we have something like polyethene, so if the polymer is given to us like this, in exam questions, normally the repeating unit, you'd have to include 2 of the carbons. So you would write out half of this. Now we're going to look at drawing a monomer from a section of a polymer. So this is actually quite simple. And what we do is we just work backwards from drawing a polymer from a monomer. And so if we've been given a polymer like this, so say we have 4 carbons and then a hydrogen and a fluorine. So say we've been given this polymer. What we do to get the monomer is just attach the double bond back. So the first thing we do is we separate it into the 2 monomers but without the double bonds. And then we just break these 2 bonds, and so the double bond reforms. And so what we get is we have carbon, double bond carbon, and then hydrogen attached to carbon, and then another hydrogen, and then fluorine and hydrogen. So this is the monomer because we've put 2 of these alkenes together to form this polymer. And so it's as simple as that. Now we're going to look at the methods of disposal of waste polymers. So waste polymers can be separated into specific types of polymer for recycling, incineration to release energy, and use as a feedstock for cracking. So first looking at incineration, rubbish is burnt and the energy produced is used to generate electricity. Some toxins can be released on incineration. So for example, the combustion of halogenated plastics, so PVC, can lead to the formation of toxic acidic waste products such as HCl. And that's something really important to remember. So toxins can be released on incineration. So incineration might be good, but toxins can be released, which is bad. And modern incinerators can burn more efficiently and most toxins and pollutants can be removed. However, greenhouse gases will still be emitted. And greenhouse gases are the main cause to global warming, and so that can be bad for the environment. However, the volume of rubbish is greatly reduced, so that is an advantage of incineration. And then looking at recycling, it saves raw materials. So nearly all polymers are formed from compounds sourced or produced from crude oil, and so it saves these materials that are quite hard to get. And then polymers need collecting and sorting, which is quite an expensive process in terms of energy and manpower. Polymers can only be recycled into the same type, and so careful separation needs to be done. And this leads into the expensive process in terms of energy and manpower again. And thermoplastic polymers can be melted down and reshaped, which is a good thing because we can make different things. And then finally, looking at feedstock for cracking, polymers can be cracked into small molecules which can be used to make other chemicals and new polymers. So this saves raw materials. Chemists have actually designed ways to remove toxic waste products like HCl before they are emitted into the atmosphere. The waste gases from the incinerator are scrubbed or reacted with a base or a carbonate because they're both alkali. And the base reacts with the acidic HCl gas, neutralizing it. So for example, here we have calcium oxide reacting with acidic HCl gas to form calcium chloride and water. And so we've neutralized it by doing an acid-base reaction. And chemists have also developed biodegradable and compostable polymers. Biodegradable polymers can be made from substances such as maize and starch. Now we're going to have a look at some questions. So for question 1, alkenes can be polymerized to produce polyalkenes. For A, state the type of polymerization that alkenes undergo. So the polymerization that we've learned about is addition. And this is when we add up loads and loads of alkenes to make a very long chain molecule called a polymer. So we call them polyalkenes. And then for B, name the alkene that gives a polymer with a repeating unit shown. So if that's a repeating unit, then that means that the polymer looks something like this. So you've got hydrogen and a methyl, and another hydrogen and a methyl, and a hydrogen, and so on. So this would be our polymer. And so we actually didn't need to draw this out, but to be able to look at the polymer and to try and deduce the alkene from the polymer. So what we do is we have a look at the small section here, at just the repeating bit, so the repeating unit. And what we do is we break the bonds, so we break this bond, and then we form a double bond. So we get a carbon with a double bond, and then we have a hydrogen and a methyl, and another methyl, and a hydrogen. So this is the alkene that we get. So now on to naming. In the longest chain we've got 4 carbons, and so it's some kind of butene, and we can see that this double bond is on the second carbon, because if we label it like this or like this, the smallest number for the double bond will always be on the second carbon, and so this is butene. And now how they've drawn it is that if we divide it up horizontally, we can see that the 2 substituent groups which aren't hydrogens are opposite each other, and so this is actually an E-butene. So before I move on to question 2, feel free to click off the video and try it for yourself first. So alkenes are the building blocks of synthetic addition polymers. Consider the hydrocarbon G, and we have CH3 to CH3, which can be polymerized. And for A, draw the repeating unit of the polymer. So first let's draw out the alkene that we have. So we have 2 carbons, and then we have a methyl group and another methyl group, and then a hydrogen and another methyl group. And so if this was to form a polymer, what we would get would be carbons, and then we'd have a methyl and another methyl and a hydrogen and a methyl, and then this would repeat, so we're adding 2 of these alkene molecules together. And so this is what we would get if we were to add 2 of them together, the polymer. And so we see that the repeating unit is actually half of this because it repeats. And so the repeating unit is carbon, carbon, methyl, hydrogen, another methyl, and another methyl. So this is our repeating unit. And then for B, draw the structure of an isomer of G which shows EZ isomerism. So because it says EZ isomerism, we definitely know that it has to be an alkene. So it has to have a double bond. And then because it's EZ, we also know that the 2 substituents which are not hydrogens have to be different, because otherwise it would be cis trans. And so we have different substituent groups. And so we work with the formula. So we've got C5H10, and so we have to make up an alkene. So if we draw out the double bond first, so that's taken 2 carbons. So we've got 3 carbons left, and that means that if we put a hydrogen here and a hydrogen here, then we'll be left with 3 carbons, so then we can put an ethyl group in, so C2H5, and a methyl. And this will give us C5H10, and this molecule will show EZ isomerism. So the way I've drawn it here will be the E isomer, because if we divide it in the middle, then the 2 substituent groups are on opposite sides. Whereas if I drew it like this, then this would be the Z isomer. Then finally for C, draw the structure of an isomer of G which does not react with bromine water. So we know that in the presence of alkenes, bromine water will go from orange-brown to colourless. And so we don't want it to react, and so we don't want alkene. So we've got the formula C5H10. And now we have to think about what other things there are that have this general formula of CnH2n without it being an alkene. And the answer is that we have cycloalkanes. And the reason that bromine water reacts with alkenes is because of the double bond. And cycloalkanes don't have the double bond and so won't react with the bromine. And so therefore, if we draw cycloalkane, so we've got 5 carbons, and that means that we have 10 hydrogens and so this gives us what we want because it won't react with bromine water, but it also has the molecular formula of C5H10, and so it's an isomer.